Hello, in this lecture we'll find out the area of the green triangle. In the drawing we have a quarter circle. A or B is a quarter circle. Inside the quarter circle we have line segment PQ that is equal to 3 units. Line segment AQ equals to 5 units. And this angle APQ equals to 90 degrees. Our mission is to find out the area of the green right triangle AQO. So first of all we will focus on the right triangle APQ. Again, we focus on the right yellow triangle APQ, and we'll implement on this right yellow triangle the Pythagoras theorem. So, in the right yellow triangle APQ, here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, the hypotenuse in the right yellow triangle APQ is AQ. Therefore, the square of the hypotenuse is AQ square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to PQ square plus AP square. Repeat again, according to the Pythagoras theorem, in the right yellow triangle APQ, AQ square equals to PQ square plus AP square. AQ is 5, therefore AQ square is 5 square. That is equal to PQ square. PQ is 3, therefore PQ square is 3 square, that is 9. Plus AP square. AP is unknown, so we leave it as it is. So, according to the Pythagoras theorem, we found out that 25 in the right triangle APQ, 25 equals to 9 plus AP square. Here we'll subtract 9 from this equation, and we'll get that 25 minus 9 is 16. 16 equals to AP square. Here we take out of this equation, and finally we get that AP equals to the square root of 16, that is 4. Square root of 16 is 4. So AP equals to 4. PA or AP equals to 4 units in its length. OAB is a quarter circle, and we can easily complete the quarter circle to a circle, and then point O will become the center of the circle. And we have the rule that a perpendicular from the center of the circle towards any chord bisect the chord. Repeat again, rule number 2. According to rule number 2, a perpendicular from the center of a circle towards any chord bisect the chord. Point O is the center of the circle. From point O, we draw a perpendicular towards chord BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O in chord BC as M. So according to this rule number 2, the perpendicular OM bisects chord BC. That is to say, OM divides it into two halves. Divides chord BC into two halves. The first half is BM, and the second half is MC. The cross BM equals to MC. Now we will implement rule number 2 in our drawing. From point O, that is the center of the circle, we draw perpendicular on chord PA. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord PA as M. According to rule number 2, the perpendicular OM bisects chord PA. PA equals to 4 units, therefore the first half PM will be equal to 2 units, of course, and the second half MA will be also equal to 2 units. In the next step, we define the intersection point between perpendicular OM and bisegment QA SN. We'll define this angle as theta, and if we focus on this triangle, right yellow triangle AMN, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. This is the sum of the angles in any triangle. Likewise, if you focus on the big yellow triangle APQ, this triangle, we have this angle is equal to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we prove that the small yellow triangle AMN is similar to the big yellow white triangle APQ. Okay, so the big triangle APQ is similar to the small triangle MNA. So why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this angle APQ in the big triangle is equal to this angle AMN in the small triangle. And both angles are equal to 90 degrees, therefore they are equal to each other. Repeat again. Angle APQ in the big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, angle theta is a common angle that belongs to both triangles. So angle theta equals to itself. We will call to angle theta two different names. In the big triangle, angle theta equals to angle APQ. In the big triangle, angle theta equals to angle PAQ. And it is equal to angle theta itself. In the small triangle, angle theta is angle MAQ. So it is a common angle that belongs to both triangles. Repeat again. Angle theta is angle PAQ, and we can call to angle theta also angle MAN. So it is a common angle that belongs to both triangles, so angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle AQP, this angle in the big triangle, is equal to this angle ANM in the small triangle. Repeat again. Angle AQP in the big triangle equals to angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we prove that all three angles in the big triangle are correspondingly equal to all the three angles in the small triangle. Therefore, we prove that the two triangles are similar to each other according to angle similarity rule. So we write it down. The big triangle APQ is similar, this is the sign of similar, to the small triangle MNA according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle are correspondingly equal to all the three angles in another triangle, then you actually proved that the two triangles are similar to each other according to angle similarity rule. And from the fact that the two triangles are similar to each other, we will derive that the following relationship exists between their sides. That PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is also equals to QA in the big triangle over NA in the small triangle. So I will write it down. PA over MA equals to PQ over MN equals to QA over NA. Repeat again. PA over MA equals to PQ over MN equals to QA over NA. PA is 4, MA is 2, and it is equal to PQ that is 3 over NN that is unknown, and it is equal to QA that is 5 over NA that is unknown. So in conclusion, found out that 4 over 2 equals to 4 over MN equals to 5 over NA. From this equation, we will derive that 4 over 2 equals to 3 over MN, so I will write it down. 4 over 2 equals to 3 over MN. 4 over 2 is 2, so 2 equals to 3 over MN. We multiply this equation by MN, and finally we will get that 2 times MN equals to 3. We'll divide this equation by 2, and finally we will get that MN equals to 3 over 2, that is 1.5. The length of line segment MN is 1.5 units. So I write it down in the original drawing that MN equals to 1.5 units in its length. From the same equation, from this equation, we derive that 4 over 2 equals to 5 over NA. Repeat again, 4 over 2 equals to 5 over NA. Four over 2 equals to 5 over NA. 4 over 2 is 2, so 2 equals to 5 over NA. We multiply this equation by NA, and we get finally that 2 times NA equals to 5. We divide this equation by 2, and we get that NA equals to 5 over 2, that is 2.5 units. We found out that the length of line segment NA is 2.5 units. So I write it down. The length of line segment NA equals to 2.5 units. NA equals to 2.5 units. What is the length of line segment QN? From the drawing, it is very easy to see that the length of line segment QN is QA minus NA. Repeat again, QN equals to QA minus NA. QN equals to QA minus NA. So QN equals to QA that is 5 minus NA. NA is 2.5. So 5 minus 2.5 is 2.5. So in conclusion, found out that QN equals to 2.5 units in its length. 2.5 units in its length. This line segment QN equals to 2.5 units in its length. We know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. Therefore, we'll block the right hand triangle AQO by a circle. So I will copy the right triangle AQO and we'll block it by a circle. So actually, this is the right triangle AOQ that I copied from the original drawing. Now we'll block this triangle by a circle. So inside this circle we have peripheral angle AOQ that is equal to 90 degrees. Peripheral angle AOQ equals to 90 degrees, and we have rule number 5 that says that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. I'll repeat again. Rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. We have peripheral angle ABC that is equal to 90 degrees, therefore it rests on the diameter of the circle that is AC. We implement rule number 5 in our drawing. We have here peripheral angle AOQ that is equal to 90 degrees, therefore it rests on the diameter of the circle, that is to say QA is the diameter of the circle. QA is the diameter of the circle. And we also know that the diameter of any circle equals to 2 times the radius for one side, but on the other side QA also equals to 5 units according to what is given us in the equation. And from this equation we get that 5 equals to 2R. We will divide this equation by 2, and finally we will get that R equals to 5 over 2, that is 2.5 units. So the radius of this circle is equal to 2.5 units. In the next step, I will copy point N from the original drawing to our drawing. This is triangle AQO, and this is also the same triangle AQO, so I can copy point N and I will place it exactly where it is here in our drawing here. So this will be point N that I copied exactly to the same place where it is located on AQ. This is the diameter of the circle. Line segment AN equals to 2.5 units in its length. Line segment NQ equals also to 2.5 units in its length, as you can see here, because of the fact that QA is the diameter and line segment AN equals to 2.5, exactly like the radius that is also equals to 2.5. Therefore we will conclude that NA is the radius of the circle. Likewise, NQ is located on the diameter QA and it is equal to 2.5, exactly like the radius of this circle that is also equal to 2.5 units. Therefore we will conclude that QN must be the radius of the circle. Where is the center of this circle? According to the rule, the center of any circle is located at a point where the diameter is bisected into 2 halves. Okay, again, the center of any circle is located at a point where the diameter is bisected into 2 halves. QA equals to 5 units. The diameter of the circle is 5 units in its length. and Qn equals to 2.5 units, and it ends at point N. So this is the first half, and the second half is NA. That's also, of course, equals to 2.5 units. So the diameter QA that is equal to 5 units is bisected into two halves at point N. Therefore, point N is the center of the circle. Point N is the center of the circle. Another reason that point N is the center of the circle is because of the fact that the diameter of any circle is located at a point where the radii touch each other. This radius AN ends at point N. The radius QN also ends at point N, therefore point N is the touching point of those two radii, and the touching point is the center of the circle. We have two reasons why point N is the center of the circle. We join points N and O together by a straight line. So point N is the center of the circle, point O is the point of the circle itself. Therefore, NO is the radius of the circle. This is exactly the definition of radius. So so NO is the radius of the circle that is equal to 2.5 units. So here NO is the radius of the circle that is equal to 2.5 units in its length. In the next step, I will copy the right triangle AMO in a new page and we will implement on this right triangle the Pythagoras theorem. Side AM equals to 2 units in its length. What is the length of side MO, triangle AMO? From the drawing, it is very easy to see that MO equals to MN plus NO. Again, MO equals to MN plus NO. MN is 1.5, NO is 2.5. Therefore, in total, MO equals to 1.5 plus 2.5, that is 4. So actually, this is the right triangle AMO that I copied from the original drawing. AM equals to 2, MO equals to 4. Here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, AO square equals to MA square plus MO square. So AO square equals to MA square. MA is 2, so MA square is 2 squared, that is 4, plus MO square. MO is 4, therefore MO square is 4 squared, that is 16. So in conclusion, found out that AO square equals to 4 plus 16, that is 20. We'll take a root out of this equation, and finally we'll get that AO equals to the square root of 20 units. AO, write it down in the original drawing, that AO equals to the square root of 20 units. In the next step, I will copy the right green triangle AQO in a new page and we will implement on this right triangle the Pythagoras theorem. The hypotenuse AQ equals to 5 units. and side AO equals to the square root of 20 units. So actually, this is the right green triangle AQO that I copied from the original drawing. By PT is the version for Pythagoras theorem. According to the Pythagoras theorem, AQ squared equals to AO squared plus QO squared. AQ is 5, therefore AQ squared is 5 squared, that is 25, and is equal to AO squared. AO is square root of 20, therefore AO squared is square root of 20 squared, that is 20, plus QO squared. Here we will subtract 20 from this equation, and we get that 25 minus 20 is 5, that is equal to QO squared. Here we will take out of this equation, and finally we get that QO equals to the square root of 5 units. Here QO, this side QO equals to the square root of 5 units. Now it is very easy to find out the area of the green right triangle AQO. Here the square brackets is the sign for the area. It means the area of triangle AQO equals to the area of any triangle equals to the base of the triangle times the height to the base. The height must create 90 degrees with the base over 2. The base, we choose the base as QO. And therefore the height to the base must be AO. Why? Because it creates 90 degrees with the base QO. So the height is AO over 2. Finally, here the base is QO, the height is AO over 2. QO is square root of 5. AO is square root of 20, all divided by 2. QO is square root of 5, AO is square root of 20 divided by 2. We have the algebraic identity that states that square root of A times square root of B equals to the square root of AB. We use this trigonometric identity here. According to this trigonometric identity, we get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 over 2. 5 times 20 is 100, so inside the root we left only with 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. So finally we found out that the area of the green triangle AQO, the green right triangle AQO, equals to 5 square units. Repeat again. The area of this green right triangle AQO equals to 5 square units. In the next step I will summarize the lecture. In this lecture we found out the area of the green right triangle AQO. It's given us the question that line segment PQ equals to 4 units in its left, line segment AQ equals to 5 units in its left, and this again angle APQ equals to 90 degrees. Again, our mission is to find out the area of the green right triangle AQO. We focused on the right triangle the right yellow triangle APQ, and we implemented in this right triangle APQ the Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AQ, therefore the square of the hypotenuse is AQ squared. It must be equal to PQ squared plus MA squared. Repeat again. It must be equal to PQ squared plus PA squared. Repeat again. According to the Pythagoras theorem in the right yellow triangle, AQ squared equals to PQ squared plus AP squared. AQ is 5, therefore AQ squared is 5 squared, that is 25, and it is equal to PQ squared. PQ is 3, therefore PQ squared is 3 squared, that is 9, plus AP squared. We subtracted 9 from this equation. We found out that 25 minus 9 is 16. 16 was to AP squared. We took out of this equation and found out that AP equals to the square root of 16, that is 4. So AP equals to 4 units in its length. Then we know that OAB is a quarter circle, we can easily complete the quarter circle to a circle, and then point O will become the center of the circle. And we have the rule that a perpendicular from the center of the circle towards any chord bisects the chord. I repeat again on rule number 2. According to rule number 2, a perpendicular from the center of a circle towards any chord bisects the chord. Point O is the center of the circle. From point O we draw perpendicular on chord BC. This angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord BC as M. So the perpendicular OM bisects chord BC. So BM will be the first half and MC will be the second half. Also BM equals, of course, BM equals to MC. You can use, you can implement rule number 2 in our drawing. From point O, we draw perpendicular on chord PA. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord PA as M. According to rule number 2, the perpendicular OM bisects chord PA. And because of the fact that PA equals to 4 units, the first half will be PM, that is 2, and the second half will be MA, that is also 2. Then we define the intersection point between the perpendicular OM and the line segment QA as M. Then we define this angle as theta. If we focus on the small right triangle MNA, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. Exactly according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, we focus on the right triangle APQ. In this right triangle, we have this angle that is theta, this angle that is 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Then we define the intersection point between chord line segment AQ and the perpendicular MOSN. We already did it, and we proved that the small triangle AMN is similar to the big triangle APQ. So why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So here, angle APQ in the big triangle equals to angle AMN in the small triangle, they are both equal to 90 degrees, therefore they are equal to each other. Then, in addition, this angle theta is a common angle that belongs to both triangles, so angle theta equals to itself. Angle theta is angle AQP, and it is equal to itself. Angle theta it is also angle ANM. Angle theta is angle PAQ, and can be called, angle theta also can be called as angle MAQ. It is a common angle that belongs to both triangles, so angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle AQP in the big triangle is equal to angle MNA in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually we proved that all three angles in the big triangles are corresponding equal to all the three angles in the small triangle. Therefore, they are similar to each other according to angle similarity rule. And repeat again, the big triangle APQ is similar to the small triangle MNA according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if we prove that all three angles in one triangle are corresponding equal to all the three angles in another triangle, then the two triangles are similar to each other according to angle similarity rule. From the fact that the two triangles are similar to each other, we will derive that the following relationship exists between their sides. That PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is also equals to QA in the big triangle over NA in the small triangle. I'll repeat again. PA over MA equals to PQ over MN equals to QA over NAN. PA is 4, MA is 2, PQ is 3, and MN is unknown, QA is 5, and NA is unknown. So found out that 4 over 2 equals to 3 over mn equals to 5 over na. From this equation we derive that 4 over 2 equals to 3 over mn, again 4 over 2 equals to 3 over mn. 4 over 2 is 2, so 2 equals to 3 over mn. We multiply this equation by mn, and finally we found out that 2 times mn equals to 3. We divided this equation by 2, and finally we found out that mn equals to 3 over 2, that is 1.5. So this line segment mn equals to 1.5 units in its length. From the same equation, this equation we will derive that 4 over 2 equals to 5 over na. Again, 4 over 2 equals to 5 over na. 4 over 2 is 2, so 2 equals to 5 over na. We multiply this equation by na, and found out that 2 times na equals to 5. We divided this equation by 2, and finally we found out that na equals to 5 over 2. 5 over 2 is 2.5. So line segment na, this line segment na equals to 2.5 units in its length. What is the length of qn? From the drawing it is very easy to see that qn equals to qa minus na. Again, qn equals to qa minus na. qn equals to qa minus na. So qn equals to qa, that is 5, minus na is 2.5. So it is 5 minus 2.5, that is 2.5. So in conclusion found out that line segment qn equals to 2.5 units in its length. Then we know that any triangle can be blocked by a circle. Any triangle can be blocked by a circle, therefore we blocked the right triangle AQO by a circle. So this is the right triangle AQO that I call it from the original drawing, and we block this triangle by this circle. Inside this circle we have peripheral angle AOQ that is equal to 90 degrees. And we have rule number 5 that says that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. Repeat again on rule number 5. According to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Peripheral angle ABC equals to 90 degrees, therefore it rests on the AC, that is the diameter of the circle. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle AOQ that is equal to 90 degrees, therefore it must rest on the diameter of the circle. That is to say, QA is the diameter of the circle. And the diameter of any circle equals to 2 times the radius from one side, but we know that QA also equals to 5 units according to what is given us in the equation. From this equation we derive that 5 equals to 2r. We divided this equation by 2 and found out finally that 5 over 2 is 2.5. So the radius of this circle equals to 2.5 units in its length. This is the right triangle AOQ. We copied this right triangle from the original drawing. This is the same right triangle or AOQ. So actually we copied angle N exactly to the same place in this drawing, exactly where it is located on the diameter AQ. So this point is exactly this point N. It is located on the same place on the diameter AQ. So we know that, so we found out that AN is 2.5 and Q is equal to 2.5. Here AN equals to 2.5 and Q also equals to 2.5 units. But we just right now found out that the radius of the circle also equals to 2.5 units. AN is located on the diameter QA and it is equal to 2.5 units, exactly like the radius that is also equal to 2.5 units. Therefore, NA or AN must be the radius of this circle. Likewise, we have NQ that is equal to 2.5, exactly like the radius that is also equal to 2.5 units. Therefore, NQ must be the radius of this circle. Okay. Now, where is the center of this circle? According to the rule that the center of any circle is located at a point where the diameter is bisected into 2 halves, we know that the length of the diameter QA is 5. 5 over 2 is 2.5. So the first half of the diameter is AN, that is 2.5. The second half of this diameter QA is NQ, that is 2.5. That is to say, at point N, the diameter QA that is equal to 5 units is bisected into 2 halves. Therefore, point N is the center of the circle. Another reason why point N is the center of the circle, because the diameter of any circle is located at a point where the radii touch each other. The radius AN starts at point A and ends at point N. The radius QN starts at point Q and ends at point N. That is to say, point N is the touching point between the two radii, therefore, according to the rule that I mentioned, point N is the radius of this circle, is the center of the circle. Point N is the center of the circle. We have two reasons why point N is the center of the circle. So we join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is the point on the circle itself. Therefore, NO, this is exactly the definition of a radius. Therefore, NO is the radius of the circle, that is equal to 2.5 units. Okay? So we can write down here that NO is the radius of the circle, that is equal to 2.5 units in this knife. Then I copied the right triangle AMO in a new page and implemented on this right triangle AMO the Pythagoras theorem. Side AM equals to 2 units. What is the length of side MO? MO equals to MN plus NO. That is to say, MO equals to MN, that is 1.5, plus NO, that is 2.5. 1.5 plus 2.5 is 4. Therefore, MO equals to 4 units. Again, I'll repeat again. This is the right triangle AMO. That is, I copied from the original drawing, and repeat again that MA equals to 2 units, MO equals to 4 units. According to the Pythagoras theorem, in this right triangle AMO, AO square equals to MA square plus MO square. Again, AO square equals to MA square plus MO square. So AO square equals to MA square. MA is 2, so MA square is 2 square, that is 4, plus MO square. MO is 4, therefore MO square is 4 square, that is 16. So AO square equals to 4 plus 16, that is 20. We took out of this equation and finally found out that AO equals to the square root of 20 units. AO equals to the square root of 20 units. In the next step, I copied the right triangle AQO from the original drawing in this new page and implemented in this right triangle AQO the Pythagoras theorem. This is the right triangle AQO that I copied from the original drawing. The hypotenuse AQ equals to 5 units itself, and AO equals to the square root of 20 units. Here by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, AQ square equals to AO square plus QO square. Again, AQ square equals to AO square plus QO square. So AQ is 5, so therefore AQ square is 5 square, that is 25, plus AO square. AO square root of 20, therefore AO square square root of 20 square, that is 20, plus QO square. We subtracted 20 from this equation and found out that 25 minus 20 is 5, so 5 equals to QO square. We took out of this equation and finally found out that QO equals to the square root of 5 units. Here, this side QO equals to the square root of 5 units. Now it is very easy to find out the area of this green right triangle AQO. The squared brackets is the sign for the area. It means the area of triangle AQO. The area of any triangle equals to the base of the triangle times the height to the base. The height must create 90 degrees with the base over 2. So we choose the base as QO and the height as AO. Why the height is AO? Because it's 90 degrees with the base QO. This angle equals 90 degrees. Again, the base is QO, the height is AO over 2. QO is square root of 5. AO is square root of 20 divided by 2. We have the algebraic identity that the square root of A times square root of B equals to the square root of AB. According to this trigonometric identity, we will get that the square root of 5 times square root of 20 equals to the square root of 5 times 20. 5 times 20 is 100. So inside the root, we left with 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. So finally, we found out that the area of this right green triangle AQO equals to 5 units. Again, the area of the green triangle AQO equals to 5 square units. Okay, thank you very much.